last lecture about conduction, and next week we're going to move over to convection. Talking about which convection, there's one good news. You take it as good news. Remember, in the beginning of the semester, I was giving you an outline of what is to come, and I was saying that besides your practical lab, there's going to be a heat exchanger simulation. That simulation lab is not going to be conducted in Glasgow, so respectively, we cannot conduct it in Korea. The reason for that is because the lecturer left the university together with everything else. Including the teaching assistant also left. So there's no one else to do that in Glasgow, so they are not going to do that simulation lab. But you're not going to miss anything because you're still going to have your heat exchanger practical lab. So that heat exchanger practical lab, you'll be grouped in fives, not any fives, but I'm going to group you guys up in fives. So this grouping will be made known to you pretty shortly. You to see from your timetable, that I think is going to start sometime in week 8. Yep. So around week 8, that time, you'll start to have your respective lab sessions. In the past, some students came in late or didn't turn up at all because for some reasons they didn't know that they should turn up. There's no makeup lab. Right? There's not going to be makeup lab because we're using Neon Poly's facilities and they have their own labs to run as well. So it's very difficult for us to plan any additional labs. So please come for the labs that you are allocated. Okay? If you have trouble, serious trouble with that, and I'm talking about serious trouble, and your allocated lab, talk to me. So let's get started. We're interested to look at the transient conduction because we're after this thing that's called the non-capacitance model. So what you have heard so far seems to be a block of material with temperature difference, and due to that temperature difference, heat will get transferred from one surface to the other surface. That's what you have been hearing. And I extended that to the cylindrical form, and even for the cylindrical form, you have two surfaces of that cylindrical pipe, the inner pipe surface and the outer pipe surface. Whenever there's this temperature difference between these two surfaces, heat will get transferred. And heat transfers from hot to cold side. But what I haven't mentioned is that how much time will it take for that heat to get transferred over? Right? It's almost assuming that there's temperature difference, so heat get transferred. What about the kind of time taken? So this is why we call it the transient conduction within an object. And we're interested to look at the conduction that's within an object, say a very, very hot object. You drop that hot object, say a metallic steel ball. And drop that steel ball into quenching water. That is cool water. Drop it into that and you hear because it's so hot. 500 degrees Celsius, drop it into water, it seizes. That kind of sudden change in the temperature requires time for stabilization. So there is this heat that's within that metallic ball at 500 degrees Celsius. It will take some time for it to cool down to achieve that steady state between the hot ball and the water. So that time taken for it to cool down is in electronic terms capacity effect. So it has a certain capacity. But if you're not familiar with this electrical circuit, when we talk about capacitor, capacitor is a device that as you apply your electrical supply, it will take some time for the capacitor to charge up to the voltage before it's considered a two-way connection. So it will take some time for it to charge up. That time factor has got that capacitance effect. So as we drop something into, let's say, a volume of water that has very different temperature compared to that object, to that volume of water, if that is a very huge temperature difference, it's very likely that you will experience capacity effect. But there's one better scientific way for us to figure that out. We don't just look at the temperature, we look at what is that material property, we look at what is that convection heat transfer coefficient, which we label it as H. Thermal conductivity, we label it as K, that is the material property of that solid. So if the conduction within the object is much faster than the heat conduction across the boundary of the object, so you have that boundary of the object going out into the water via convection. If there is this huge disparity, then it's very likely that you're dealing with a transient conduction effect. So that across the boundary, the Newton's cooling law is one example of that. We'll have a closer look. And we use a number, BIOT, Biot number. Biot number is a number that helps us to decide can we use the lung capacity method or not. What is a lung capacity method? That will come in the subsequent slides. But for any of this sudden quenching in a cool environment, you would need to calculate what is the Biot number. So what is the Biot number? The Biot number is given by this formula, where the H stands for your heat transfer coefficient for your convection side. The V here stands for the volume of that object. The A here stands for the surface area of your object. And then the K over there is your thermal conductivity of the object. So if you put this, arrange it in that way, and do the calculations, and see that it is lesser than 0.1. If it's lesser than 0.1, that means you could use the lung capacity method. Lung capacity method will be used in the subsequent slides. But if this Biot number is less than 0.1, what that means is that that surface convection is actually larger than the internal conduction that's going on in the solid. Now, what does that mean? This is an example of those two cases where Biot number is less than 1 and Biot number that is high. So high would be a lot more larger than 1. So in the case of Biot number that's less than 1, could you see that heat within this is temperature scale? So this axis here is temperature, that axis here is distance. And I have a solid object in here, and I place this solid object into, say, water that is at the temperature T infinity. And if you look at this temperature scale, T infinity is actually at over this point. This point is not 0. There's a temperature axis. So it's a lot more lower. T infinity is a lot more lower. And if you look at the solid temperature distribution within the solid, this being the midpoint of the solid, you'll be able to see that at the midpoint of the solid to the edges of the solid, that temperature difference is actually not too much. Compared to the temperature difference between the solid surface to T infinity, that temperature jump from here to here, this temperature jump is a lot more larger. So Biot number that's less than 0.1 would have this kind of characteristic, where the temperature distribution within the solid is very small, but the temperature difference between the solid surface to T infinity will be large. Conversely, if I have zooming view of the internal part of this solid body. And I compare this temperature difference between the center of the solid to the edge of the solid over here. This temperature difference now is a lot more larger than the convection temperature difference. It's a lot more smaller. So in those cases, you'll find that the Biot number will be huge. But then the question is that, how huge is that? We know that if Biot number is less than 0.1, then it means that we can use lung capacity method. That one we'll have a look at it later, what is lung capacity method. But we didn't say that when Biot number is large, how large it will be. Right? Typically, you'll get in a region of about 5 and above. Right? How about 1? If I have Biot number that's equal to 1, can I use lung capacity method? The answer to that is that the larger the Biot number, starting from 0.1 and above, the larger it is from that, the lesser you could use your lung capacity method. So then where is that point? The point is that it is less than 0.1, and in fact, actually most of the questions that you will get that after calculating your number is going to be less than 0.1, so then you can conclude that you can use the lung capacity method. So what you have seen just now, the thermal resistance of the heat transferred to the object is larger. So if I were to sketch out that horizontally, you get that to be delta T over the thermal resistance, say across a slack of a block, that's delta H over KH. Now the one in the denominator, that is your thermal resistance, R TH, thermal resistance. Now if thermal resistance were to increase, and if I have a constant heat transfer rate, what do you think would be the temperature difference delta T? This would increase, this one got to be decreasing so that you can have a constant heat. Now if delta T is going to be decreased, that means we are looking at a case where within the solid, the temperature difference is going to be small. And if the temperature difference within the solid is small, it's very likely that your number is going to be less than. So this thermal resistance also will play a role in deciding if you have a lower Biot number that's less than 1. So this part here says that Biot number got to be less than 1 for a solid object. Then the entire material will be of the same temperature, roughly of the same temperature internally. And if Biot number is less than 1, then it's an accurate approximation for our intergenesis, of which we'll be using the lung capacity. So if you have various layers of material, you need to find out the individual lung and the individual Biot number in order to decide that. So each of these individual layers, Biot number got to be less than 0.1. So you can have a whole system of many resistive and capacitive elements cascaded together in a sequence. Let's look at what is a lung capacity. Electrically, is actually the schematic form is sketched out in metal. I want you to be able to see two things. One is the solid side, and the other one is the liquid side. The solid being the conduction side, and the liquid being the convection side. Do you remember the Newton's cooling law? Q equal to HA delta T. Right? That's a Newton's cooling law. I can express this in terms of the thermal resistance for the conduction part by taking that HA to the bottom. So 1 over HA is my thermal resistance for convection. So if you see 1 over HA, that's my thermal resistance as a result from the convection. So this part here, convection. And this part here is actually where our solid is, and that is where we experience conduction. But why is the conduction side a capacitor? It's a capacitor because I was talking about this object being placed in a fluid environment suddenly. So that's quenching effect, that's capacity effect. And because of that capacity effect, we have to bring in this bond capacity model. So the model is given by this equation over here. And what I'm going to do is to slide over here to prove from this stage to that stage. I'm going to make use of this figure over here. Right? I'm going to make use of that figure over here. And this figure, I'm going to assume that T naught is greater than T infinity. So T naught here would be the surface temperature of that solid, and T infinity would be the temperature of the water that's in the infinity. So obviously your object that we're talking about is not very hot, so T naught is larger than T infinity. So we're going to start with that. I'm going to write out this equation over here. Q equal to HA T minus T infinity equal to minus rho CV dt d tau. And tau over here is actually a time in terms of seconds. I know I could use the symbol T as well, but in the textbook, consistent with the textbook, we use the symbol tau to represent time. So I'm going to do something with this set of equations. I'm going to separate the variables. Separating the variables. You have taken your mathematics bridging course. Yep. Did they talk about differentiation? Talk about separating the variables, or sometimes they call it variable separable. Yep. If it doesn't ring any bell, no problem. I'll walk you through. This is how it's going to work. I have this part here, dt, d tau, that I want to separate this variable. This is not a fraction, this is differentiation. So I'm using a technique to split up that differentiation symbol. That differentiation symbol can be separated using the variable separable method. So this is how I'm going to do it. HA T minus T infinity d tau. So I'm going to bring d tau over minus rho CV d T minus T infinity. So if you're wondering, hey, this is supposed to be just dt as what I could see over there. Well, actually, these two terms, there's no difference. Why there's no difference? Because T infinity is a constant. T infinity is the temperature of the water toward the infinity, and that is a constant number. If I differentiate T minus a constant, if I were to differentiate that, that's actually equal to T. Right? Because you differentiate term by term. So if you differentiate a constant, you get what? What do you get if you differentiate a constant? You get 0. So if I differentiate this term over here, it would be dt, and differentiate this is 0. So I'll get back dt as what I could see over here. So So these two terms are actually equivalent. The next thing I want to do is to bring this term over to the right hand side. I'm going to write everything on the left hand. So I have this dt minus t infinity divided by t minus t infinity equal to everything else on the right hand side. So I'll have minus HA over rho CV d tau. So rho over here is the density of the object. C is the specific heat capacity that we heard from last lecture. And V is the volume of your object. Now, by the way, those symbols, they are labeled over here, so we can see what all those symbols mean. So continuing, I want to integrate both sides using the following initial conditions. What are the following initial conditions? My initial conditions is that when time is equal to 0 seconds, my temperature is equal to T0, that's the surface temperature. That's my initial condition. The other initial conditions that I have are kind of like a general condition. Tau equal to tau, and T will be equal to T at time tau. So it's kind of like your time, your temperature is dependent on time. So it's sort of like the general equation. I'm going to make use of that, and then to integrate the left-hand side, integrating this left-hand side, I'm going to write it out in the following way. And from the limits of T0 to T at any temperature tau, this will be equal to this right-hand side minus HA over rho CV. The entire thing is a constant. Integrating d tau from 0 to tau. Now the question is, how do I integrate this left-hand side? Integrating the left-hand side, what do I get at? If I ask you, if I integrate 1 over x dx, what do you get? You get ln x. So this is kind of like 1 over x dx. So what I'm going to get is ln, so-called x will be t minus t infinity. And you have the limits from T0 to T tau equal to minus HA rho CV. How about integrating d tau? What do you get from there? If you integrate 1, what do you get? Dx. Integrating 1 with respect to x, you get x. Integrating 1 d tau, you get tau. So tau from the limits of 0 to tau. So now I could substitute the limits into it. So ln t here would be t tau minus t infinity divided by t0 minus t infinity. Now how do I get this one from substituting the limits? That's because if I substitute the limits, I get ln t tau minus t infinity minus ln t0 minus t infinity. So according to the law of indices, if I have a ln minus ln, it's actually ln this term divided by the next term. Let's go logarithmic law. So we can write that down. So that's how I got to that fraction. Minus HA over rho CV. And this tau will be just a tau symbol. So now the next thing that I want is to express this term here in the bracket as the subject. If I were to do that, I'll be taking inverse ln on both sides. So So I get E to the power minus HA over rho CD. So that's a proof of it. And you could see that it is this equation here that you need to know. This equation is the equation for lung capacity model. Right? What is it as lung capacity? You could see that it would have the capacitance. What is the capacitance? The capacitance is actually from your diagram. From your diagram, your capacitance is actually over here. That is rho CD. That is your capacitance of your system. Why is that capacitance in your system? That's because your system is suddenly quenched in cool water, and you need some time for it to achieve steady state. That some time is defined as it has certain capacity effect. That's why it's sketched out in that way. So let's have a look at an example. This example, let me do the sketch of this example. It's talking about a steel ball with the following characteristic. I'll draw the ball over here. And it says that this steel ball has the specific heat capacity 0.46 kilojoules per kilogram degree Celsius. That's a unit for specific heat capacity. It also says that this steel ball has conductivity. That's 35 watts per meter degree Celsius. Right? And it also says that this diameter of that steel ball that would be not a disc, the ball is a spherical shape. So that steel ball has a diameter of 5 centimeters, and its surface initial temperature is that it has a uniform temperature that is 450 degrees Celsius. And it also gives you the ambient T infinity temperature. That one is at 100 degrees Celsius. And it also says that convection that's across the surface of that steel ball, that convection H is given by 10 watts per meter squared degree Celsius. And the question asks you to find what is tau at the temperature of 150 degrees Celsius. The question asks you to find that out. So obviously, if it has got to deal with time, tau being the symbol for time, then we have to figure out, can we use the lung capacity method or not? In order to figure that out, your Biot number is going to help you figure that out. So the Biot number, Bi, has the formula HV over A divided by K. That's a Biot number equation. So what I'm going to do next is to fill in all those variables. HK, now the volume and the area. Volume and the area, you got to figure out what is the volume, the equation for the volume of your sphere. Do you remember the equation to that? For sphere, the volume is equal to 4 over 3 pi R cubed. How about area? For the surface area of the sphere, what is the surface area? You have ready? Is 4 pi n r. Gotta be square. Why gotta be square? Because area is meter square, right? So the only variable over there is radius. If you cube it, then it's volume, right? So, yeah, we've done that before in education. These kind of formulas, they're not right. Surface area, volume, whatever shapes, because these are considered too fundamental. University level, look at that, and hey, why are you testing with that? I know all this stuff. So, you need to know. So I'm going to fill in the B and the A over there. So for the H, I have it as 10. The volume, that will be 4/3 pi r. And R would be 0.5 centimeters. That's for the diameter. So for the radius, that will be 2.5 centimeters. And in meters, that will be 0.025 cube. Divide by that area, 4 pi. I'll move this away. 4 pi 0.025 squared. Divide by k value is 35. If you're to solve that, you will get 0.0023. And is this lesser than 0.1? Lesser than 0.1. Hence, we could use the lump capacity method. That is applicable. Right. So if we can use lump capacity method, which is actually just talking about this set of equations, it's just talking about this set of equations. We have all this T infinity, T naught, and everything else. So I'm just going to list it down that you have T that is 400. Sorry, you have T here, the T that you want to achieve. There's 150 degrees Celsius. You have T infinity that is 100 degrees Celsius. You have T naught. T naught is the surface temperature, 450. You have things like your density of the steel, although it's not given in the question, in the exam will be provided to you. You don't have to memorize that one. The density of the steel, 7,800 kilograms per meter cube. H, that's given. And C, that is 460 joules per kilogram degree Celsius. So now let's plug it all into that equation at the top. But I just want to solve this part first. That's the HA over rho CV, because that one has a lot of numbers in there. So I'm going to substitute it in. That will be 10, and the surface area, that will be 4 pi r squared divided by rho 1,800 specific capacity. And the volume, that will be 4/3 pi r cubed. If you just solve that one, you get to 3.344 times 10 to the power minus 4 seconds to the power minus 1. Right? That's the unit for that. If you do the units cancellation, you get that to seconds to the power 1. So now that I have that, I can put it in. What I need is T minus T infinity over T naught minus T infinity equal to e to the power minus this term HA over rho C and multiplied by tau. So if I put everything in, that's a final temperature that I want to achieve, 150 degrees Celsius. T infinity, that's 100. T naught, 450. T infinity, 100. E to the e to the power of minus 3.344 times 10 to the power of minus 4 and tau. I hope you're able to find what is that unknown tau from this equation. If you couldn't, please come to me. You just need to take that ln on both sides. Yeah? Take ln on both sides. Eventually, you're going to get tau that's equal to 5819 seconds, or that's about 1.62 hours. So this is a part that was in an exam last year. Not sure will it come up again this year. Last year there are a lot of this initial part of the lecture as part of the exam question. Okay, let's go on to beyond 1D conduction. So far, we heard about steady-state conduction, transient conduction, but all these conduction is only in one direction. That means 1D. So beyond 1D, let's look at the two-dimensional conduction structure. So for two-dimensional conduction, if you haven't finished copying, you will come down later. I'll let you get access to this. I need to do a setup, and this setup requires this two-dimensional plate labeling. So I'm going to label my two-dimensional plate in the following way. This point over here, this point, that, and that. These are actually called nodes. They're called nodes. So you have one center node, and these four respective nodes that are surrounding it. I'll call the center node with the coordinate MN. This is the coordinate MN. Right? So that coordinate MN. The size of the grid in this y-axis, I call it delta y, that is distance between here to here. Delta y, I'm assuming to be of a unique value, that is equal to 1. The same goes for my delta x on the x-axis, that resolution. I assume that it has a unique value that is equal to 1. So this node over here would share the same coordinate of m. So you can see that m stays. But the one that's above this will be n plus 1. And the one that's below it will be n minus 1. So the same goes for these two nodes that are beside the center one. The one on the left-hand side, you get n minus 1, comma n. And the one on the right-hand side, that's n minus 1, comma n. So this is how I'm going to label my coordinates. Here's this 1, 2, 3, 4, 5 points. I'm going to take an example to show you how to establish a set of equations that deal with 2D conduction. So let's have a look at this shape over here. Now this shape over here has got this surface, this entire surface over here that's at 500 degrees Celsius. And this entire surface here at 100 degrees Celsius. This surface, entire surface over here, 100 degrees Celsius. And this entire surface over here, 100 degrees Celsius. I'm going to do this first note first. Looking at note number 1, right? You got to follow very closely here, because if you miss that first part, it's actually hard for you to understand what's going on for the rest. So stay with me very closely. Let's have a look at this first note. This side, the temperature here is 100. And what I'm going to do is to take the difference between the temperature. So the difference between the temperature, 100 minus T1. 100 over here. Why is it 100? Because the surface is at 100 degrees Celsius. So I'll take 100 minus the temperature. At this node, I call it T1. And then I look at the top here, 500 minus T1. So 500 minus T1. So just now was 100 minus T1. And this node over here, T2 minus T1. T2 minus T1. And this node over here at the bottom of T1 is T3 minus T1. So if I were to take all those differences, add them together, the resulting temperature will be equal to 0. It has to be equal to 0. If it's not equal to 0, that means that node is generating some temperature. But that's not the case, right? This is just a solid. So whatever temperature differences that are coming in gonna be the same as whatever temperature differences they are going out. That's why you could sum it all up and they'll be equal to 0. So I could simplify this equation over here. There's 100, there's 500 over there. So I'm going to take it out. There's T1, there's minus T1, minus T1, minus T1 here, and minus T1 here. So there's minus 4 T1. There's a T2 over here, so it's going to stay. There's a T3 over there, it's going to stay. So this one I could simplify it to be 600 plus T2 plus T3 minus 4 T1. 0. That is for node 1. If I were to look at node 2 now, so I'm going to write out node 2 over here so it's easier to see. So for node 2, what I'm going to do is to do the same thing. I'll take T1 minus T2. T1 minus T2. Add that to the next one, 500 minus T2. 500 minus T2. Plus the next one, 100 minus T2. 100 minus T2. And the next one, T4 minus T2. And equate the whole thing equal to 30. Later on, I'll tell you why I am establishing this set of equations. So if I were to simplify this, what you're going to get is you have 500 plus 100 over there. Yep, so you get 600, and I'm going to simplify it, plus T4 plus T1 minus 4 T2 equal to 0. Let's have a look at node 3 now. So for node 3, we're going to do the same thing. There will be 100 minus T3. Plus T1 minus T3. So this will be T3, this is T4. T1 minus T3. Plus T4 minus T3. Plus this side here, 100 minus T3. Do that simplification, you get 200 plus T1 plus T4 minus 4 T3 equal to 0. For node 4, it's still going to be the same thing. T3 minus T4 plus T2 minus T4 plus this surface 100 minus T4 200 minus T4. If you were to simplify that, you get to 200 plus T3 plus T2 minus 4 equal to 0. This is equation 1, equation 2, equation 3, and equation 4. Out of these 4 equations, T1, T2, T3, and T4, they are all unknown. 4 unknowns, 4 equations. You can use simultaneous equation and solve that. So if you use simultaneous equation to solve that, you get to T1 equal to T2, that's equal to 250. And then T3 equal to T4, that's 150. The next thing that I want to look at is this method that I was just outlining. That one allows you to find out respectively within a solid with the side temperatures what will be the respective breed temperatures of T1, T2, T3, and T4. This method allows you to find it out. If you're wondering, is there a faster method? Actually, there is. If you're interested to find out the temperature of a certain node, so the certain node would be having the other nodes that are surrounding it. So I'm going to let, say, for example, just labeling for labeling purpose, T1, T2, T3, T4. If I'm interested to find out what is this node temperature, say I call it T naught, what I need to do is to add up all this. So T1 plus T2 plus T3 plus T4. Add up all that and then minus 4 times of that T naught and equal to 0. That's a shortcut. Right? That's a shortcut. That is actually a formula that we can use. So if you want to find the temperature of a certain node, you just add up all those at the 4 sides. Add them up. Minus 4 times of that node temperature that you're interested in. Is it true? Let's have a look. Say, for example, node 3. So node 3, if you want to find out that temperature, you should add T1 plus T4 plus 100 plus 100 minus 4 times of T3. So 100 and 100, that will be 200. So T1 plus T4 minus 4 T3. Yeah. So, okay. So we could use that formula, right? So you can use this one. Use this formula for identifying what's the temperature of certain nodes. Now the other thing that I want to cover is the heat transfer rate, that is Q. Now remember your Fourier law of conduction is given by this. And this Fourier law of conduction, I could simplify it into the following form. That is Q equal to K A delta T over delta X, where X is actually the distance that heat is transferred across, that's the thickness of the object. So in our case, that X over there would be our y-axis, because we're considering that's the thickness along the y-axis where heat is transferring across, and then the x-axis, that's delta X, that's located over here. So this one, in this figure, we'll have it as K delta X multiplied by 1, because this one we assume that it has a unique depth. This figure over here has a unique depth. That's why I multiply by 1 over here. So that the area will be delta X multiplied by the depth. That's the heat. That's the area where heat is transferring across. And delta T over delta Y. Where delta Y is this one, delta X, that is delta X. So if I want to find out heat that's transferring across a certain surface, then I need to sum up all of that. I need to sum up all of that. And this is a summation sign, right, given by this symbol over here. So I need to sum up all of that. So again, I'm going to try to find out for that 500 degrees Celsius surface, what will be the delta T. So the delta T for that surface will be taking, we have these normal 1, 2, 3, 4 temperatures ready, so I'm just going to write it down. This 250, this 250 degrees Celsius. Load 3, that's 150 degrees Celsius. Load 4, that's 150 degrees Celsius. So the temperature difference across this part over here, that will be taking 250 degrees Celsius minus 500. So 250 minus 500. And then over at this surface, 250 minus 500. And we're going to assume that delta X and delta Y, they are all equal to 1. So if I have that using this set of equation, I'm able to find out what is Q. So Q will be summing up K. A in our case is delta X multiplied by 1. And we know that delta X is actually equal to 1. Is actually equal to 1. And for your temperature difference, delta T, we have already found it out, is 250 minus 500 plus 250 minus 500. Right, that was from here, delta T. Divide by delta Y. Delta Y in our case, we assume it to be unique value as well. So 250 minus 500 plus 250 minus 500, that will be minus 500. That's why your Q will be equal to minus 500. Okay, that's I mean, so that minus, because your Fourier's law has got a minus. Right? So your Fourier's law has a minus, so it becomes plus 500K. Okay? Because your Fourier's law has a minus over there. So let's have a look at the other three 100 degrees Celsius bases. So these are one, this is one, that's one. So the same thing, I'm going to take the temperature difference along that three surfaces. So for this side over here, that will be 100. That will be 250 minus 100. 150 minus 100. 150 minus 100 here. 150 minus 100 here. 150 minus 100. And 250 minus 100. That will be my delta T. And if I substitute it again,